PEACH stands for Processes Driving Exchange at Cape Hatteras. The overall goal of PEACH is to understand the exchange of waters between the shelf and the deep ocean. Cape Hatteras is in a really unique position where you have shelf waters in the South Atlantic Bight flowing northwards towards Cape Hatteras and Middle Atlantic Bight waters flowing southwards towards Cape Hatteras.
Our primary question is how does water move across the very narrow, shallow continental shelf here and reach the deep ocean? Or conversely, how do nutrients and things that life in the coastal ocean need, how do those cross the shelf from the deep ocean into the continental shelf shallow water? By shallow, I mean from the coast here on out to the shelf edge, which is 60 meters deep, something like that.
The Gulf Stream is a western boundary current, and I think it's been a very well-studied western boundary current. Obviously, Benjamin Franklin was very interested in it in the late 1700s. It's certainly an important feature for ship navigation. It's very important for climate there because it carries heat from the tropics up to the mid-latitudes there. It keeps Europe warm, which is a very good thing. But also there is a lot of marine life around the edges of the Gulf Stream there, and certainly there's a very strong recreational fishing industry in North Carolina there. And one of my big concerns scientifically, and why I'm so excited about this project, is there really has been recent changes that get me concerned about how the continental shelf circulation works.
We have a whole array of different instruments that are being used together that are in the water now. We're going to be linking that up with measurements that are taken from shore or from satellites. And we are looking at waters from depths of, let's say, 20 meters, so 60 feet, down to depths of a couple of miles. So there's a whole range of spatial scales and temporal scales that are of interest here. This project has researchers whose expertise is in different areas of the ocean. It has researchers from all different institutions, all coordinating together to answer this question of how these different parts of the ocean interact with one another.
Here on the Armstrong, the vessel that we're on now, it's kind of like a toy store for scientists because it has the most up-to-date research tools and equipment. Some of the favorites of physical oceanographers like us are the acoustic Doppler current profilers that we use to measure currents beneath the vessel. And there are 3 on the Armstrong. There are 3 different frequencies. And so we use all 3 of those simultaneously to measure the currents under the boat as we move around on the shelf and across the Gulf Stream so we can measure the current velocities. One of the tools that's like the workhorse tool for oceanographers is called a CTD, and a CTD measures the water's conductivity, temperature, and depth. And the conductivity is how we measure the salinity of the water. So once we have the salinity and temperature at a certain depth, we have a good idea of the water density, and that tells us a lot about the physics. We tend to have these different density water masses that are meeting, and so we're interested in how they mix or don't mix and how they interact together.
One of the relatively new ways of measuring currents is with shore-based radar systems. And with this system and several others we're installing, we'll be measuring from about up near Avon, around the corner at Cape Hatteras, down to Ocracoke Island. And we hope to get measurements of surface currents at about a mile increments from here all across the shelf. We think we will find very complex circulation here because of all the things blowing the water around. And we think we will be able to measure those at very short spatial scales. And that will be a brand new way of looking at this area in terms of circulation.
We have these instruments called PIs, that's pressure sensor equipped inverted echo sounders, and we are deploying 4 of them across the Gulf Stream downstream of Cape Hatteras. And then we're deploying some along the Gulf Stream upstream of Cape Hatteras. Basically, the PIs are telling us about the strength and position of the Gulf Stream.
A spray glider is one kind of autonomous underwater glider that profiles up and down through the ocean by changing its buoyancy. It moves oil in and out of the pressure hull to change its volume, thereby rising and falling through the ocean. And as it does that, it's able to move forwards by pitching its nose down as it's sinking and pitching its nose up as it's rising, and using wings to translate that vertical motion into forward motion. Our spray gliders carry sensors for measuring temperature, salinity, chlorophyll fluorescence, the currents using acoustics, and also acoustic backscatter.
The more we understand about the world, the more we can help protect our resources, exploit our resources responsibly, invent new things that improve our everyday lives. More directly, in the recent past, there have been signs of changes in the ocean on a large scale. And so if we can understand how the circulation affects things that matter to humans, like the composition of the atmosphere, whether carbon dioxide is being removed efficiently at Cape Hatteras, whether there will be an infinite supply of nutrients to support phytoplankton and the food web higher up so that we can continue to reap from the ocean as we have in the past. Every bit of information helps humans respond responsibly to their desires to use and exploit coastal resources.